Hi everybody and welcome to a new video in the Deep Learning for Audio with Python series. This time we're gonna try to tackle overfitting. So specifically we're gonna look into techniques that we can use to identify overfitting and then to solve it. Cool. So if you guys remember last time we built a multi-layer perceptron that's able to do music genre classification, but we had an issue, and the issue was overfitting, which basically means that the model was doing very well on the training set, but it was having issues with data it had never seen before. Right, so first of all, what we want to do is find a way of identifying overfitting. And for doing that, we can use a couple of plots that are very informative. So it's basically taking a look at the accuracy and the error of both the train set and the test set over time, over all the epochs and training cycles. So for doing that, obviously we need to retain information about the training process. And fortunately for us, TensorFlow has a super duper way of doing that. And so if we look at here, when we train the model, we just do a model.fit. You should know this by now, guys. And if you don't, just go back and watch my previous videos on this. But the return of this fit method is a history object, basically, that retains information about the accuracy and the error of both the train set and the test set over time. Cool. So we can just store that information doing a history equal to this thing. Now, the next step that we want to do is basically to plot the accuracy and error over the epochs. Now, we don't have this function yet, but we'll fake it for the time being. And so we would say plots history. And obviously we'll pass in this history argument. Cool. So now we should build this plot history function. So we'll define it over here. So we'll do a define plot history, and as we know, plot history accepts an argument. We'll call it history. And so here we need to build this plot. Well, we want to build a plot with a couple of subplots, right? So one is for the error and the other one is for the accuracy. But for building plots, as we know, we need to use matplotlib, which is this super interesting and super cool a library for plotting, and we need to import that, right? So we'll do an import matplotlib.pyplot, and we'll import that as plt. Right, so here what we want to do is we'll get a figure and an axis, and we'll do a plot.subplots, and we'll pass in 2. So basically what this does, it returns a figure object and this axis over here, and we'll say that we want 2 subplots, right? Okay, so as the first step, let's create the accuracy subplots. Okay, so let's say, the accuracy subplot is going to be axis in 0. And here we need to plot the stuff that we want to plot, right? And so here we want to plot, first of all, the accuracy of the train set over time, right? And then the accuracy of the test set. So here we know that the accuracy of the train set is stored in a dictionary called, not surprisingly, history, and the key is accuracy, right? So it's not really that surprising, but it's quite straightforward. Right, and we want to associate a label to this, and we'll just call it train accuracy, right? And now we are just going to duplicate that line, and instead of the accuracy, we want the train accuracy, which is stored as val accuracy, right? And so the label in this case is going to be called test accuracy. Cool. So now we want to set the the name of the y-axis, right? And so that is going to be a set y label, and this is accuracy. Good. So now we have the y label. Next thing, we want to just like place the legend so that we can read the legend. And so we'll do a axis0.legend. And here we have an argument that's called location, and we'll say that we want this in the lower right corner. And finally, we want to set a title. So we'll do a set title, which is going to give a title to our subplots. And the title, not surprisingly, is going to be accuracy eval. Right. And so this way we have all of our subplot for the accuracy. Now we can just like take this, copy, and just change a few things around to create the error subplot. Right, so here this is not 0 anymore, this is going to be 1. And then here we don't want to retrieve the accuracy, we want to retrieve the error, which is indicated here. It's stored as loss. Now, if you've been watching my videos, you know, guys, that I prefer error to loss, but unfortunately the guys at TensorFlow think it differently. Cool, so the label here is going to be train error. Then we want to retrieve the error for the test sets. So we'll do a val underscore loss. And then the label is going to be test error over here. And then we'll set the way label, and this time to error. And we want to locate the legend in the upper right corner. And you'll see why that's the case in a second. And the title is going to be error eval. And then, yeah, let's just put an X label here. We'll set the X label, and obviously the X label is epoch. Cool. So now we have the two subplots, but we still need to show them. So we'll do a plot.show. That's great. Okay. So now we should have everything in place. So I'm going to run this script that's going to use the music genre classifier that we built last time. And so we'll see how to identify overfitting looking at these two very important plots. Cool. So now I'm going to run the script. It's going to take some time, so I'll just pause the video and take it back. And here we are back with the results of the training process. So as you can see here, guys, we have this nice plot of the accuracy over time, and the overall like accuracy for the train set is quite high. And as you can see over time, it basically went all the way up, almost like to 100%. Remember, guys, like this down here are all like epochs, and we have like 100 epochs, right? But for the test accuracy, we just like go up, and then we just like stale at around like 60%. So as you can see here, there's a huge difference over time in the test accuracy compared against the train accuracy. And so that is in itself a huge indication of overfitting. Now let's take a look at the error evaluation subplot as well. And here we have like a similar thing, right? So we have the train error that obviously like goes down over time. It becomes like very like little, whereas like the test error goes down for quite a while, and then it just like remains like unchanged, and then it actually starts to increase again, right? So this again is another indication that our model is hugely overfitting. So now the question is, how do we solve this issue? Because obviously we want for our model to be able to generalize to data it has never seen before. Well, it turns out that there are a bunch of different techniques that we can use. So let's take a look at a few of those. So here we have 5 that I listed. So we have simpler architecture, data augmentation, early stopping, dropout, and regularization. Now, I'm going to implement in TensorFlow only dropout and regularization, but I'm going to talk about like all of them, right? So let's start from the first one, which is also like the simplest, probably also nice to understand. Here, the whole point is that if we have a model that's like overfitting quite a lot, perhaps what we want to do is to try having a simpler architecture. So, and how do we achieve that? Well, we can achieve that by doing a couple of things. First, we can remove layers. So if we have, for example, like 4 or 5 hidden layers, we can go down to 3 or 2. And then we can decrease the number of neurons that we have in each layer. And the reason behind this is that like the more complex the architecture and the more the architecture, the more the model is going to be able like to actually interprets like all the patterns and getting like and learning everything also like beyond what's like generalizable, and all like the I would say like also like the artifacts and nuances of the train set like itself. So by going with a simpler architecture, we kind of like remove all of that, and that basically means that the model is going to be probably like more likely to perform better like on more general data. So this is like the first option that we have to fight against overfitting. Now you may be asking, but how do I do that? So what is a simple architecture? Well, there's really no universal rule here. So you have just like to play around with stuff and see like what works for you. What I usually do is I start with relatively simple networks with few like layers and few neurons, and then I just like add them up in order to have like a model that's like more powerful, like, and it's able like to express like and to learn the complexity of the data. Cool. So this is about using a simple architecture. Now we have another option, which is called data augmentation. In our case, we're going to do audio data augmentation. And here, the whole idea is basically, it's quite simple, right? And it's basically like the more data you have and the better your model is going to perform, both on your train set, but hopefully also like on your test set, which is basically all the data that the model has never seen, right? But sometimes it's very difficult to get like extra data. So what we want to do is we want to artificially build new training samples, right? And for doing that, what we can do is we can apply transformations to our train set, to all of our training samples. In the case of audio, what this basically means is to, for example, apply certain transformations like pitch shifting. So where we just like move the pitch either up or down. We can also like time stretch. So we basically change the speed like of the audio file, or we can add background noise. And so in that way, we are able like to just like recreate artificial versions like of the original like training samples, and so that we're going to have like more data, which hopefully is going to kind of like prevent us from overfitting. Now, there's a whole art and science about audio data augmentation. I'm not going to get into the details, but the whole point is you apply a bunch of light transformations, and obviously you can combine also those. So for example, you can combine pitch shifting with time stretching, or you can add noise and then time stretch an audio file, right? But the whole point is to create a lot of like new data that is somehow related to the original one, but then it has way more training samples. Now, the important thing to remember here is that when we do audio data augmentation, we want to use like we want to do it like directly on the train set. So we don't want to do audio data augmentation the whole data sets and then use the augmented data also for testing purposes, because otherwise there you are cheating a little bit, because I mean, at the end of the day, the transformed data is somehow related to the like original data, right? And so you want to keep the augmented data only for training purposes, so that when you work on the test set that is like a completely unseen batch of data for the model. Right, so this is like the second technique we have. Then we have a third one, which is like quite heuristic based and quite simple to understand. It's called early stopping. And so here the whole point is that we want to choose certain rules to stop the training. And so for doing that, let's look at the error like plot down here, right? So in blue we have the train error, and then in orange we have the test error, right? So basically with early stopping, for example, in this case, we could say, hey, if the test error doesn't improve after, I don't know, let's say 7 iterations, then just stop the training, right? And so here you can decide how many epochs you want to wait before you stop, and obviously you can also like decide how much like is the improvement that you want to like expect, right? And so like in this case, as you can see, this is like very, very handy because we are stopping training before we start overfitting, because as you see after that the test error remains like more or less stable, whereas the train error goes down, which is like a typical signal indication of overfitting, right? So this is for early stopping. Now we have another couple of very useful techniques to fight against overfitting. The first one is called dropout. So dropout is a technique that enables us to randomly drop neurons while training. And by doing that, we increase the network robustness. So how does that work? So here we have down here we have like our network, right? So now when we train, say for example, we have like the first like batch of data in. So we may decide to randomly drop certain neurons. And so here, for example, we have like these 2 neurons like in gray, which have been dropped. So all the connections like don't work for these neurons. And so the training just happens like through like the remaining part of the network, right? And so now like with the second batch of data, for example, we could just like change the neurons. And this is going to be done like randomly, stochastically, right? We have a certain probability of dropping neurons in a layer. So here, for example, we drop this neuron in this second hidden layer and we restore like the previous neurons, for example, right? And the question here is why does this work? So what's the point of all of this? Well, it turns out that if we do this, we are increasing the network robustness because the network can't rely on specific neurons like too much. So all the neurons have to take somewhat responsibility of the prediction process, right? Because sometimes like some of these neurons don't exist. And so like the neuron, the network has to kind of like reshape and re-give responsibilities to all of the neurons so that none of them is like indispensable, right? Cool. So now there's a hyperparameter here that's called the dropout like probability. And now again here there's really no universal rule. And this so usually like what you would use like is anything between like 10 to 50% of drop-in neurons like in different layers, right? But again, it's somewhat connected to like your problem. So you have to figure out like what works for your problem specifically, right? So this was dropout. And now we have a final technique that's called regularization, right? And so this technique is very interesting and very effective, and it basically adds a penalty to the error function. And basically the whole point is that we want to punish large weights. And so the larger the weights and the higher like the penalties like that we're gonna give like to the error function. So here we have a couple of types of regularizations that are usually used in deep learning, L1 and L2 regularization. So let's take a look at them like in specifically one by one. Okay, so here we have L1 regularization. So here the whole point is that we want to minimize the absolute value of the weights. Now down here, you can recognize the error function, quadratic function that we've used like so far, like in our theoretical discussion of neural nets. Now these we have like the quadratic error here, and then we add this regularization thing. And now, as you can see here, we have like the sum of all like the weights, or the absolute value of the weights. And then we have lambda, which is like the term, the regularization like term. So the larger lambda, and then the higher like the penalty that we give to the network. Obviously, lambda is another like hyperparameter that we need to tweak in order to like optimize our network, right? So L1 regularization is really good because it's robust to outliers, and it kind of like generates simpler models like overall. Now we can also use L2 regularization, and the difference with L1 regularization is that we minimize the squared value of the weights, and you can see it here. And because we do that, L2 regularization is way less robust to outliers. But the great thing about L2 regularization is that it can learn quite complex patterns. So I already know that what you want to ask. So should I use L1 or L2 regularization? Now, again, this is kind of like more an art than a science, but the overall like rule a thumb that I can give you here is that if you have like data, kind of like relatively like simple to train, simple to learn data, probably you should go with L1. But if you have like data that's kind of like, I don't know, that's a little bit like more complex to learn, the patterns are more complex, then go with L2. I would say like that in most audio and music based deep learning tasks, you usually want to use L2 regularization. Cool. So now we have an overview of all the different techniques that we can use for fighting overfitting. Now let's just go back to the code. So we can easily implement dropout and regularization using TensorFlow. Well, it's as easy as it can be, really. So for dropout, we are going to implement it for all the hidden layers. So for doing that, we'll just do a keras.layers.dropout, and then we'll pass in the dropout probability, which we'll set to 30%, so 0.3. Good. So now I'm gonna copy this and just paste it below the second and third hidden layer, and dropout is done. Cool. What about regularization? Well, for regularization, we need to pass in an extra argument to these dense layers. So we'll do it for hidden layer 1, 2, and 3. Cool. So the extra argument is called a kernel regularizer, and we just need to call keras.regularizers. We'll do an L2 here. And if you guys remember, L2 has a hyperparameter called a lambda, which is kind of like the penalty multiplier, and we'll put it to 0.001. Cool. So now I'll just like take this and paste it for hidden layer 2 and 3. Great. We've done our, basically we've implemented our way of like solving overfitting for this music genre classifier. So we should just like see if this works. And in order for doing that, we need to rerun the model and take a look at the plots of the accuracy and the error. So I'll see you in a second. Here we are with the results of our training process, and as you can see from the accuracy and error plots, things are going quite well. We've basically almost completely solved, prevented overfitting from happening. And so let's take a look at the error plot down here. So I'm just going to zoom in to take a look at this. And as you can see here, the error of the test is quite comparable to the train error up until, like, I would say, like, yeah, epoch number 70, and then like the train error is going down, whereas like the test error is remaining more or less the same. And we can see that issue also in the accuracy subplot over here, like around, like, yeah, I would say like epoch 70, we start having the train accuracy going up and the test accuracy stabilizing, which basically means we are overfitting a little bit, but overall we basically like solved overfitting here. If we wanted to do like even a better job, we could use like some early stopping that probably would stop like the training process around like epoch 70. Cool, but this is great news because now we know how to fight against overfitting, and as we've seen, dropout and regularization work really, really well. Cool, so the next time we're gonna look into a more complex type of neural network called a convolutional neural network that's been used like for like image data quite a lot, but it's also very, very useful on audio data. So stay tuned for that. I hope you've enjoyed this video. If that's the case, please like it and consider subscribing. So if you have any questions, please leave them in the comment section below, and I hope I'll see you next time. Cheers.